Hello and welcome. Today, in this part of the video lecture, in the course Programming for Problem Solving, I am Sandhya and we will discuss about a searching technique called as binary search. Okay, we know that searching is a process in which we try to find out if a particular element is found in a list or not. So we have already seen one of the searching technique called linear search, and today we will look at binary search. So what is binary search? Binary search is little quicker than linear search. However, it cannot be applied on unsorted data. It requires a sorted list to work on. So binary search is a technique based on divide and conquer. Okay, so what is divide and conquer? Divide and conquer is a programming strategy or a programming paradigm in which you tend to, take out a big list or a large list and try to divide it into smaller parts, execute the smaller parts and try to get the solution to integrate all of them to get the solution for a larger problem. The process of dividing a problem into subparts and then executing to get the answer is known as divide and conquer programming strategy. So how does binary search work? Binary search starts by testing the data in the center of the array, determines the target either it to be in the first list or in the second list. Imagine before we start, let us assume that we are having our textbook and I want to open page number 30. Let us assume that I want to open page number 30. So when I wanted to open page number 30, it is implied that, whenever we just take off a textbook like this, we don't always end up at 30. Case one, we might end up, just like that. When I open, I might directly come into 30 page number, where the page number that I'm searching for is found in a single go. This is usually said to be the best case. I'm searching for something and I just like that found it. That is the best case. Coming back, there are now two chances. I wanted to open page number 30 in a 200 pages textbook because I know that 30 will come somewhere at the starting. I just picked up like this. I ended up being at page number 20. When I know that I'm at page number 20, you don't look at the first 20 pages, you skip the 20 pages and again concentrate on the rest of the pages and again pick some other page to search. So here is a case where I shelved some part of the data and concentrating on the remaining part of the data. That means it is evident from this example that binary search, searches only few elements. Each time it discards some elements. Okay, so now imagine case 3. What is the possible case 3? Case 3 is in a context where I wanted to open page number 30, but I ended up opening page number 50. But I know from page number 50 to whatever comes in the other half are clearly useless because page number 30 does not fall in the later half. So therefore, I leave out all that later half and concentrate only from page number 1 to 50. So this is case 3 where I assume that my data is in the first half of the list. In case 2, my data falls in the second half of the list. And in case 1, my data is just there when I searched it for. So this is how the binary search tends to work. So therefore, it's evident that binary search, has fewer comparisons than linear search. So therefore, how does it get executed? The key is compared with the middle item. And if the key matches with the item, you just return the middle index and then stop. Otherwise, if the key is less than the middle positioned element, then the item is expected to be found in the first half of the array. So you tend to concentrate only on the first half of the array. Whereas on the opposite side, if not, then you tend to concentrate on the second half of the array, expecting that your element is found in the second half of the array. So what is the idea of binary search? The idea of binary search is to assume that the list lies in between lower boundary and upper boundary, where lower boundary is set to 0 and upper boundary is set to n-1. And you repeat the process 4 and 5 until you're done or until your lower boundary crosses upper boundary. Okay, so lower boundary and upper boundary are inclusive boundaries and your data is expected to be in this middle, in between the lower boundary and the upper boundary. Once your lower boundary crosses over upper boundary, implies that you have finished searching the list. So therefore, clearly the element is not to be found. So in that case, we return match not found. Otherwise, if the data is in the limits of lower boundary and upper boundary, you tend to see if your key is equal to A of middle. If so, you will return the match found and return the index middle. Otherwise, if your key is lesser, then the data is found to be in the first half. So therefore, you will set your upper boundary to middle -1. Otherwise, it is expected that the key is in the second half. So therefore, you will set your lower boundary to mid +1. And the action is repeated until lower boundary is less than or equal to upper boundary. Once when this condition is false, we'll simply say that the match not found or the element not found, indicating an unsuccessful search. What are the merits or advantages of binary search? The biggest advantage of binary search is its time. Binary search is quicker than any other search. Okay, and also it takes fewer comparisons. These two are the advantages of binary search, where its standard disadvantage remains to be expecting a sorted list. So therefore, you got to have a sorted list for binary search to work on. Okay, so this is a simple iterative program where we try to implement binary search. The basic still remains the same. You read the size of the array and the elements into an array and an element to search, that is k. Okay, so if your position is -1, indicating that the search is unsuccessful and you say that your element is not found, but if the search is, not -1, that means there is a return from the function, then you say that your element is found and you will display the position. Okay, let's go ahead. And how does this work? Okay, I set my lower boundary to 0, that is the first element of the array, upper boundary to n-1, as long as upper boundary is greater than or equal to lower boundary, or in other words, lower boundary less than or equal to upper boundary. You find out your middle element by dividing your lower boundary and upper boundary by 2. If your element is lesser, you search in the first half, or else if your element is greater, you will search in the second half, or else if your element is equal, you will return the middle position. Any one of this should be true, but if the boundary crosses, implies that you're returning -1, indicating that the search is unsuccessful. So here on the screen is an example. I'm searching for 67, so 67 is here, so therefore it returns such successful. So this is a simple recursive approach. We keep everything simple, but instead of doing it again, we just keep up this return of binary search. Okay, so this is an example for for a binary search, and this is an example for an unsuccessful condition. Okay, here is an example. Let's take up this example and try to understand what does all this mean. So I'm searching for 23 in this list from 0 to 9. What is 0 plus 9 by 2? 0 plus 9 by 2 is obviously, 9 by 2. 9 by 2 is nothing but 4. So therefore, your middle is 4 as highlighted here. So check out the fourth element, 26. Fourth element is 16 and you're searching for 23. 16 is lesser than 23. That means your search element is greater. So greater elements falls in the second half because this is a sorted list. So therefore, set your lower boundary is equal to mid plus 1. Mid is 4, so mid plus 1 is 5. Now your lower boundary is 5 and your upper boundary is 9. 5 plus 9. 5 plus 9 is 14. 14 by 2 is 7. So you start comparing with your middle element 56, but 56 is a bigger element. So therefore your element falls in the first half. So your lower boundary is 5 and your upper boundary is mid minus 1. So it is 6. Now you got to choose between 5 and 6. 5 plus 6 by 2 is 11 by 2, nothing but 5 again. So you come back to 5. 5 is mid. A of I is equal to A of mid. Yes, it is true. So therefore you return mid. Mid value is 5 now. So therefore you return 23. So this is how the binary search gets to work, and this is a simple example for that. Okay, so what is the complexity of binary search? Binary search in the best case requires one comparison, but in the worst case requires log of n comparisons, log n to the base 2 comparisons. And the space complexity of binary search is constant. It just so, but when we talk about binary search, it's evident that we tend to compare with linear search. So here is a comparison between binary and linear search. Binary search works only on sorted list, whereas linear search works on any kind of list. Binary search is faster than linear search, whereas yes, linear search is comparatively slower. It takes an average of log n comparisons, whereas it takes an average of O of n comparisons, where n is the number of elements in the list. And for example, if there are a million elements, binary search just takes 20 comparisons. And for the same, on an average, it takes around 50,000 comparisons. Linear search takes around 50,000 comparisons. So before we close, dear students, I recommend all of you take a pen and a paper to write down the pseudocode and flowchart for binary search and to analyze binary search for these elements to search for 9 and 3, and also to try to figure out the best, the merits and the demerits of binary search. Also, try searching, this is a list, try searching for one. Try searching for one, dear students, in this list. Please tell me when one is an unsuccessful search. So what happens when you search for 1? 0 plus 9. 9 by 2 is 4. The element at 4 is 16. When you compare with 1, it is lesser. So search in the first half. Now the lower boundary is 0. Upper boundary is 3. Yes. So 0 plus 3 by 2 is 3 by 2. Nothing but 3 by 2 is 1. So therefore your lower boundary is 0. Upper boundary is 1. Again, 0 plus 1 by 2 is 1 by 2. Nothing but 0. So therefore check with your 0 element. 1 is lesser. So it will be in the first half of the list. Now your upper boundary is 0 and your lower boundary is, now your lower boundary is 0. And now when you search, your becomes -1. -1 is not in the list, right? -1 is not in the list. So therefore you return -1. You stop because -1 is out of index. So this is how we'll execute for both, positive, for both elements, successful and unsuccessful searches. On this note, thank you.